Yeah. So in yesterday's class we looked at box functions, right, and we saw that we could use a whole set of box functions to represent any given function, right. I was originally planning to do hat functions today, but first maybe we'll look at polynomials and functions as a means of generating basis vectors, say on a given interval, right, and see what's the problem with that, and then we'll go on to hat functions. Is that fine? So the question is, the problem that we had with the box function the problem that we had with the box function was that even for a straight line, if we wanted to approximate a straight line, we got, because our function is a constant on a given interval, we got a representation which was piecewise constants, right, and we could get as close as we want to the function that we are trying to represent, but then as a consequence the jumps that we get, the number of jumps that we get in the function representation increases, right. So we are trying to ask the question, isn't there a way for us to get something that is smoother? We have defined the dot product yesterday as the dot product of f comma g as the integral, if the functions are defined on the interval a b, as fg dx. We will see what this means if we just take an interval, again say 0 1 or something of that sort, and see what it means to the standard polynomials that we deal with, okay, and see whether we can use those to represent our functions. So consider the functions, two functions, f of x equals 1 and g of x equals x to start with, okay. Are these functions orthogonal to each other, or what is the angle between these functions? Does that make sense? So once you have defined the dot product, we can use the definition of the dot product that we had earlier from geometry, where we said that a dot b is magnitude a, magnitude b, cosine of the angle, included angle between them. We can use a similar idea and basically say that cosine of the angle between two functions would be the dot product fg divided by the norm of f and norm of g, right. Analogous to what we did with vectors, you could define a theta in a similar fashion. So the question that I am asking, so we have already used, actually we have already used the property that theta is pi by 2, we said that two functions are orthogonal, we have already done that yesterday. The question that I am asking, is it possible for us to find the angle between the functions f and g as given there, okay. So what is f dot g, what is that dot product, integral x, let us say the functions are defined on the interval, x belongs to the interval 0 comma 1, let us say we take x from on the interval 0 1, the function is defined on the interval 0 1. So it is 1 times x dx, which gives me x squared by 2 between the limits 0 1, which is 1/2. Is that fine? So clearly they are not orthogonal, What is magnitude f? Magnitude f is the square root of the integral 0 to 1 dx, which is 1, and what is magnitude g? The norm of g, the integral 0 to 1 x squared dx square root, which gives me x cubed by 3 between 0 to 1 divided by square root of 3. Is that fine? Okay. And therefore of course all of these numbers look familiar because we just dealt with something very similar in the last class, and therefore what do we get for cos theta? 1 by 2 root 3, and you can consequently find theta. So it's just an interesting exercise. You can consequently find theta. What does it mean? Anviksha, is there a mistake? Root 3 by, did I goof? I made a mistake. Oh, I'm sorry, root 3 by 2. I'm sorry, root 3 by 2. It gives a much better number, right? Gives you a much better angle. Okay, right. So, but I'm not really interested in finding theta here, right? Or I realize that theta is not pi by 2, okay? And we have already seen earlier that it is very convenient to have these functions or the basis vectors that we get to be orthogonal to each other, right? We have already seen that it is convenient to have these vectors orthogonal to each other. So given this, we will follow the same process that we did earlier and try to get two sets of vectors, two vectors which are perpendicular to each other from the 1 comma x. So 1 comma x are linearly independent, 1 and x are linearly independent. How do I get two vectors so that that angle is pi by 2? So what I do is I repeat what we did earlier. So if this is A and this is B, right? So from A, of course, I can get the unit vector A, little a, which is A hat, right? And I can find the projection of B on A. How do I find the projection of B on A? I take B dot A, okay. So B dot A gives me the projection, the component of B that is along A, right? B dot A gives me a component of B that is along A. Let me just give it a subscript B sub A. B sub A times A hat, what is that? That is a vector representation of the component of B along A, right. So if I subtract this from B, B minus B sub A, A hat, and I call that, what should I call that? I just call that B prime. What is B prime? B prime is the vector B with its projection from A removed from it, okay. So now the question is, what is B prime dot A? B prime dot A is 0. So we have managed to construct a B prime which is orthogonal to A, and from B prime I can get a, I will just call it a B hat by dividing by the magnitude of B prime, okay. So you gave me A, B to start with, and I come back with an A prime B prime, I am sorry, A hat B hat, which are unit vectors which are orthogonal to each other, okay. So you have given me one set of vectors. I have now managed to extract from that A hat B hat which are orthogonal to each other. So if I had a third function, if I had a third vector C, I could repeat this process. If I had a third vector C, what I would basically do is, from the third vector I will subtract out the B hat part, I will subtract out the A hat part, and I will be left with something that is purely C, right. If I am left with nothing, that means C was linearly dependent on the other two. Is that fine? Okay. We will do that now to the functions, we will do that now to the vectors 1 and x. So back here we asked the question, what was f dot g? F dot g was half, is 1/2. So this is this times 1. So the function that is along, that is the component of f that is along g, or g that is along f, is 1/2 if it is g along f, right, and f is a constant, and therefore if I subtract out, if I repeat the process b minus b prime a, b minus b dot a, if I repeat that process, what I am going to get is, I am going to get x minus 1/2 times 1, the basis vector is just the constant function 1, okay, and this should be now my new improved this should be now my new improved G prime. Is that fine? Okay. So can I make this a unit vector? Is it possible for me to make it a unit vector, G prime? How do I make G prime the unit vector? So what is G prime dotted with G prime? X minus 1 half squared dx on the interval on which it is defined, which is x minus half cubed between 0 and 1. And what is this? 1 half cubed plus 1 half cubed, oops, I am sorry, which equals 1/4, is that right? Into, oh I am sorry, by 3 by 3, fine, okay. And therefore G hat, G, if you want to call it G prime hat, if you want to put a hat on it just like we did for the other unit vector, or just call it G hat. G hat would be x minus 1 half, I have to divide by the magnitude, and the magnitude is 2 times square root 3. Are there any questions? That is fine. So now we have the vectors 1, 2 times square root 3 into x minus 1 half. Is that fine? These are orthonormal, the magnitudes are 1 and they are orthogonal to each other, okay. Let me add a third vector into the mix. What if I added x squared? I want to add x squared, so I define an h of x which is x squared. If I define an h of x which is x squared, and this is still on the interval 0 1, if I define an h of x which is x squared, what is G hat dotted with h? That is 2 root 3 x minus 1 half into x squared, the integral from 0 to 1 dx. Is that fine? Everyone? Yeah. So what does this integral give me? This gives me a 2 root 3 into, that gives me a x to the 4th divided by 4 minus x cubed divided by 6 between the limits 0 and 1, which is 2 root 3 times 1/4 minus 1/6. What does that give me? 1 by 2 root 3. So that is the component of h along G hat. So we repeat this process. So from h, that is x squared, I subtract out this component. So that is 1 over 2 root 3 times, what is the basis vector? 2 root 3 into x minus half. I am repeating the same process that I did here, b minus ba times a. I am repeating the same process that I did there, which of course gives me x squared minus x plus half, and there is something wrong. We have to, okay, that's fine. So what's the other thing that we have? That's x squared minus x plus half. Yeah, that's fine. So what do we have now? So we have removed the g hat component. This has removed the g hat component. So what I will call this is h hat, h prime. Now I want, from this I want to get rid of the component that belongs to 1, the function 1. So what is h prime dot f? That is integral 0 to 1 x squared minus x plus 1 half times dx, which gives me x cubed by 3 minus x squared by 2 plus x by 2 between the limits 0 and 1. And that should give me the projection of h prime on f, which is nothing but 1 by 3 minus 1 by 2 plus 1 by 2, which is 1/3. Is that fine? And as a consequence, if I subtract this out from here, I am going to get h double prime, which is x squared minus x plus 1/6 minus x plus 1/6. Okay. If I subtract a third from the half, I get 1/6. And I let you verify. You can verify that h hat in fact is 6 times the 5th root of 5 x squared minus x plus 1/6. You can just check that out, find out what the magnitude is. Please.
Because we already eliminated the f component from G, and you've taken the new h dash x prime, and then you're taking the inner product with f. Instead of that, you just take it with x prime.
Yeah.
You've subtracted the component from G, so you take inner product with f, that will go to 0 in this.
If I am taking the, no, if I am taking, you are saying do G instead of?
F instead of
Instead of G hat, you are saying do G.
no, instead of h prime f, do h f.
Instead of H prime F, do HF.
Because G prime and f prime are anyway orthogonal.
G prime and
G hat and f hat are orthogonal. So whether you take h prime there or h, it doesn't matter.
whether I take H prime there or H, it does not matter. You are saying why did not I just do x cubed instead x squared times 1, whatever it is, that is fine. Yeah. Yeah, the order does not matter. The order does not matter. What you have to basically do is you have to make sure that if you have a set of vectors that you are subtracting out this and this from X. Yeah, that is true. You could, what you are basically saying, then the expression is a lot easier. I didn't have to include that x plus half because anyway it is orthogonal. That is true. Yeah. Yeah. Because the part that I am subtracting out, you understand the point that he is making, the part that I have subtracted out here, it basically comes from, is already orthogonal to f. So there is no reason to include that in the calculation. Is that fine? Okay. Yeah, are there any questions? So you can see that excuse me, you can see that now I will call them f hat, g hat, h hat. You can see that I can actually generate a whole set of these functions. Okay, in fact I can take the set 1 x, x squared, x cubed, x to the 4th and so on, and I can generate a whole set of these basis vectors that are orthonormal, orthogonal to each other, and the magnitude is 1, right, based on our definition of the dot product. Is that fine? Okay. Now why don't we just use this? Why don't we just use this to represent our functions? Right? Why not just use this to represent our functions? So that's one question that we have. Why bother with box functions? These are nice and smooth functions. Why not just use these to represent our functions? Is that fine? Okay. Of course, if our function had a cubic variation and we took only the first 3 terms, right, we are unlikely to pick up that cubic variation properly. Am I making sense? You can see what you can go check to see what kind of an error that you would make and so on. The other problem is, just like in Fourier series, maybe we will look at Fourier series a little right now, just I am not sure how many of you are familiar with Fourier series. There is the issue of how do we, when we are hunting, remember, don't forget why we are doing this, why we are constructing these orthonormal functions, right. Just to recollect, our governing equations are differential equations, the solutions are functions. We want to write programs that will systematically hunt for the solution, which means systematically hunt for the functions. So we are trying to create a set of functions which have some structure in them so that we can search them in a systematic fashion. Okay, so such a set of functions, right, such a set of functions which have this nice structure, what is the distance between functions and so on, such a set of functions we will call it a space, a function space, a space of functions, right, and we are basically trying to construct a function space. That is essentially it. Okay, so let's see what happens. Let me we will get back. Maybe what we will do is we will do Fourier series also. We will go along and then see what's the issue with, what's the issue. Why don't we use this, right? And we do use it sometimes. Let's see what we get. Now, one of the points that I want you to check out, you can try this out now. If I take the same functions 1 x, x squared and so on, if I take the same set of functions, but now they are defined on the interval -1 to 1, does anything change? Does anything change? So what happens to f dot g? Becomes -1 to 1, 1 times x dx, which is x squared by 2 from -1 to +1, and it is 0. They are orthogonal. So the orthogonality depends on the interval in which the function is defined. The dot product is defined over that whole interval. It may be obvious, right, when you look at it, but the number of times students make a generic statement saying sine and cosine are orthogonal to each other and then integrate on the wrong interval, right. It happens to all of us, right. So you have to be a bit careful. It is orthogonal from -1 to +1, but not orthogonal on the interval 0 to 1. Okay. I would suggest that you try to do a few of these on the interval -1 to +1, just like I have gone through, right. So for on the interval 0 1, I would suggest that you try x cubed or something of that sort, just to make sure that you are able to get through on that, and then do these from -1 to +1, do a few of them. Okay, and if you have had ordinary differential equations, if you had a course in ordinary differential equations before, pay attention to the functions that you are getting and ask yourself, have you seen them before, right. You should get a familiar set of functions, right, especially if you have done a course in ordinary differential equations. This interval -1 to +1 should yield a familiar set of functions, right. Let us look at, I am not going to do Fourier series in great detail here. So Fourier series, the functions that you are looking at are of the form 1 sine, cosine, sine 2, cosine 2 and so on. They are functions of this nature. Okay. So the obvious question from this discussion, the obvious question is are the functions 1 and sine orthogonal to each other, right. So now you should always remember, you have to ask the question, on what interval are we talking, right? What is the dot product definition of the dot product, and what is the interval on which we are talking? So if you say that on the interval 0 to 1 sin of x dx not 0, right? On the other hand, if you say on the interval 0 to 2 pi sin of x dx, you do get 0, fine. So the functions 1 and sine are indeed orthogonal, on that interval, and of course you can figure out how to go about normalizing it and so on. So the point of this discussion is that the interval, the domain on which we are defining the function, is important, right, for our idea of orthogonality, just as it is important for our idea of the dot product. And of course when we are actually solving problems, when we get to the point where we are actually working on fluid mechanics problems and asking questions and answering questions in fluid mechanics, you will know what is the extent of your domain, and therefore you will know what are A and B, fine. So why don't we just use this? Why don't we just use 1x, x squared and so on? Why not just use Fourier series, right, to fit? So if I give you a function, if I give you a graph, if I give you some arbitrary graph, why not just use these polynomials in order to approximate this function, to represent this function? Why do I go through this headache of trying to find piecewise constants that will approximate the function? Okay. The idea here is that if I have my f hat, g hat, h hat that I got earlier, that I got here, if I have the f hat, g hat, a hat, I can try to find a f hat plus b g hat plus c h hat. I can try to find the coefficients a, b and c in order to approximate this function, and in adjusting these values while I am hunting for the function, any change I make to a will translate the whole graph up down. Any change I make to b will cause the slope to change. Any change I make to c, right, will cause the curvature to change everywhere. The key word is everywhere, right. So if I have this complicated function and I am trying to fit a curve to it, every time I adjust one coefficient to fit some part, the trouble is it is going to get spoiled somewhere else. It is very likely that it will change somewhere else. I do not have what is called the property of locality. I do not have this power where local changes in coefficients cause only local changes in the function. I want to be able to raise and lower this, whereas if you take this box function, it is possible for me to take this and lower it there, independent of what is happening elsewhere. I can just change the level of just at one interval, right. So the box function clearly has this property of locality. I can just change in one interval, I can change the level of that function just in one interval without affecting anything else that is happening elsewhere, okay. So this property of locality is very important. This property of locality gives me this freedom for me to adjust my solution as I go along, okay, without affecting other parts of my solution that I have already possibly adjusted to my satisfaction, right. Whereas if I do not have locality, then any change that I make is a global change, right. So if I say a sin x, if I change a, sin x is going to change. In fact, if you think about it, sin x actually is defined from minus infinity to plus infinity. So you are changing everything from minus infinity to plus infinity just by changing this a, right, total global change. Whereas what I would like to do is I would like to keep it local, fine, okay. So for that reason right now I am going to reject using f hat, g hat, h hat, right. Having gone through this effort, I basically say it is nice, I know how to do it, but I am going to reject these functions, okay. We can come back later and see whether it is possible for us to use them or not. What we would really like is we would like the smoothness that these polynomials bring and the locality that the box functions got, we would like to have the smoothness that these polynomials bring with tied to the locality that the box functions brought, okay. And therefore as a consequence, now merging these two, we are going to come up with hat functions. Okay. We are going to define this as follows. What we realize is, if we have, so from the yesterday's class we know if the support of two functions is non-overlapping, is not overlapping, then they will be orthogonal, they are orthogonal to each other. There is a reason why I repeat this, there is a reason why I write this out and repeat this. So it has only to do with the support, right. Remember, the support basically means the function is non-zero in that part of the domain, right. So it has only to do with the support, it does not actually have to do with the function value. That means that if I have, yesterday I chose functions f and g in a fashion such that the support was non-overlapping. This was f, that was g, and yesterday we basically said that f dot g, because the support is non-overlapping, it turned out that f dot g are orthogonal to each other. The question is, does it have to be a constant there? It could be anything as long as it is not 0, right. Is that fine? So since this is true, since it comes from the support, what we will do is we will try to pick one of those polynomials to do it, and to keep life easy we are going to pick the linear, we are going to pick x, right. We are going to be a bit careful here, so we pick x. So let me see if I can construct these functions in a systematic fashion. So we have some interval a b that we are interested in, right, and as we did earlier we are going to break up this interval into subintervals. I am going to focus on one particular subinterval xi plus 1, okay. So I will zoom in on that, particular interval. So what I am going to do is I am going to just zoom in on this particular interval, that is xi plus 1, and I will define two functions here. I will define two functions here. One is a function, it is basically 0 everywhere, and at xi it is 0, and it then rises from xi to xi plus 1, it goes from 0 to the value 1. I will name this function n, it is 1 at I plus 1, 0, because I am going to define two such functions. The other function is also 0 everywhere, right, just like the box function. The only difference is that it drops from 1 to 0 going from xi to xi plus 1, and since this function is 1 at xi, I will call it ni, and it is a second function, so ni1. Is that fine? Do you understand what the functions do? The blue one, ni plus 1 0, is 0 everywhere, so it is going to be 0 from a to b everywhere except on the interval xi plus 1, where it starts at 0 and in a linear fashion rises to 1. Ni is again 0 everywhere over the whole interval a b except at xi plus 1, it starts at 1 it goes down to 0, fine. Now clearly if I have two such functions, on two different intervals, if I have two such functions on two different intervals, if I have one interval here and I have another interval here, and if I have two such functions on these two different intervals, so I have one function here, and get the same blue, one function here, one function there, and one function here, one function. If I have two such functions, right, this is ni plus 1 0, ni 1, this would be nj plus 1 0, nj 1. If I have two such functions, these two functions are orthogonal to those two functions. Each of these functions is orthogonal to each of those functions. If I define such functions over all the intervals xi plus 1, in any given interval one of these functions will be orthogonal to functions in the other interval, because the intervals are non-overlapping, fine. So we use the fact that the supports are non-overlapping, therefore they are orthogonal, that is the good part. But what about the two functions to each other? The two functions obviously to each other are not orthogonal, right, they are obviously not orthogonal. So what is that dot product? What is ni 0, ni 1, I am sorry, ni plus 1 dotted with as a function of x, ni 0 as a function of x dx, the integral, it is 0 everywhere except from xi to xi plus 1. What is this function? What is this integral? So in order to do this we have to get a function form, we have to get an algebraic form for ni and nix, okay. We have to get an algebraic form for ni and nix, ni plus 1 and ni plus 1, ni plus 1x and nix, okay. So we come back here, what is ni plus 1 as a function of x? X minus xi divided by xi plus 1 minus xi, right, it has a positive slope, over the length xi plus 1 minus xi, it goes from 0 to 1, right. So at x equals xi it is 0, at x equals xi plus 1 it is 1, it is a linear function, so it satisfies, right. Again we are hunting, even here if you think about it, we are actually hunting for functions, right. I have given you a graph and we hunted and found that function, okay. And what is ni? So if this is some alpha of x, I name it alpha of x simply because, so what is ni? 1 minus alpha of x, okay. Are there any questions? Any questions? Fine. So what we do is, what we will do now is we will find out what is that, what's the dot product, what is that dot product. So ni 1 dotted with ni plus 1 0 gives me integral xi plus 1 to xi up xi to xi plus 1 alpha of x times 1 minus alpha of x dx. And what does this turn out to be? You can just check that you can just verify that that's true. So is that fine? Okay. So what do we have now? What we have now is I have defined a bunch of functions ni 0 and ni plus 1s. These depend of course on the interval. So obviously if I go to I minus 1, this is on the interval I plus 1. If I go to the interval I minus 1 to I, what will I get? The corresponding functions ni minus 1 0, ni 1. Am I making sense? If I go to the intervals I minus 2, I minus 1, I will have the functions ni minus 2 0, ni minus 1 1. Fine. On each of the intervals I will have two of these functions. What have we managed to do so far? What can we do with this? What can we do with these two functions that we have defined on the interval? So first let us just focus on this interval alone. We will just look at this interval alone. So if I take ai or a times ni 1 plus b times ni plus 1 0 as some function f of x defined only on xi plus 1. What does this give me? For any given a b, what does the graph of this look like? It has to be a straight line. It is the sum of two linear elements, and if I were to graph it, if I were to just graph f of x, remember this is the interval xi plus 1. If I were to just graph it at x equals xi, ni is 1. At x equals xi plus 1, ni plus 1 is 1, the other one is 0. So this is going to be a function that goes from a to b in a linear fashion. So if I change my b value, if I change the value of b, if I were to raise the value of b from here to some value here, then I would get a graph that looks like that, right. So I have a linear interpolant, but I also have locality in the sense that if I raise this value a b, it affects this interval, and we will see if it affects anything else. Is that fine? Okay. So ai, ani, bni plus 1 allows me to give you get a linear interpolant in the interval xi plus 1. So in general, if I had an arbitrary function f of x, I should be able to write this f of x as summation I equals 1 through n. I will just write it as 1 through n. We have to figure out what happens at the intervals elsewhere towards the beginning and end. Anyway, we will go through, we have n intervals, I equals 1 through n. What am I going to get? ai ni 0 plus bi ni plus 1 1. Is that fine? The intervals are non-overlapping, they are orthogonal. It should be possible for me to represent any function f of x in this fashion. On any given interval, the ai bi will give me the straight line interpolant between those 2 points. Okay. Let us take 2 intervals and see what happens. Let us take 2 intervals and see what happens. So this is xi minus 1, xi xi plus 1. Okay. So I have some function, and I want to represent this function using my newly developed right linear interpolants. So what I am going to do is I am going to use, let me use some colored chalk here, on the interval xi plus 1, if I take these two values to be a and b, I will get a linear interpolant that looks like that. On the interval xi minus 1 xi, what will my a value be? What is a? A is the value here, and what is b? B is going to be what was the a in the xi plus 1 interval. So in fact, though it looks like I have two coefficients, incidentally it's possible we could come up with a scheme just like in the box function. If you are willing to allow discontinuities at this interval, at the edge of this interval, at the interface between the two, if you are willing to allow discontinuities, then a's and b's can be different. But if you want the function to be a continuous function, the representation to be a continuous, which is where we are going right now, then the ai corresponding to xi, right, has to be the bi corresponding to the xi. Okay. So the a and b at this point have to be the same. Is that okay, everyone? Okay. So in fact what you have to do is we have to recombine these. So you are saying ai ni bi and I plus 1. So maybe what I should have done here was I should have made this bi plus 1 I plus 1 and I plus 1. Okay. If I make that bi plus 1, then what does that do for me? Then I can actually make the statement that ai should be equal to bi. It allows me to do that. So the coefficient here is the same, and what are the functions, what are the basis vectors ni's that it multiplies? This coefficient ai, what does it multiply? It multiplies, if this is 1, or let me lower the, let's just say this is 1, it multiplies this function. What is this function? What was this label? ni 1, and it multiplies this function, and what was its label? Did I switch it around? ni0, ni1. Did I have it right the first time around? Okay, fine. ni0, yeah, ni1. I had it right the first time around. Okay. There in the integral. Okay, I made a mistake here. Okay, that's fine. Sorry. Yeah, you guys should tell me immediately as soon as you catch it. So I have flipped it around everywhere. Thank you. Yeah, you shouldn't let me go through with this. Well, fortunately what is going to happen is I am going to get rid of those superscripts. So okay, fine. Look at the functions ni0 and ni1. ni0 and ni1 are non-overlapping. I can actually combine these two functions, I can add them up, I can literally add them up, since ai and bi are the same, ai equals bi equals same. This summation I equals 1 through n, right, since ai and bi are the same, I have to just shift this. So if I go back to when this was I minus 1, I equals 1, or if you want me to, I can write it out, but anyway it is okay. If I factor out the ai's, since the ai and bi are the same, I am going to get, what I have seen here is I am going to get an ni0 plus an ni1. That summation f of x you can open out the summation for a few terms and see that this is true. Okay, it is actually possible for me to factor out the AI, since AI equals BI, it is actually possible for me to factor out the AI for Ni0 and Ni1, and these can be added now, these can actually add, and if you add them, this is the function that you get. Okay, so this is summation I equals 1 through n AI Ni. I will rewrite this summation, I will rewrite it at the other end. So f of x can in fact be written as summation I equals 1 through n AI Ni, where Ni of x equals Ni 0 of x plus Ni 1 of x. Is that fine? 0 to n minus 1, as I said, so we will have to look at what happens through, because there is an issue. So I leave these we will investigate, I just write this just for right, so we have to really look at what happens for all these intervals. Okay, so now for so the endpoints, we look at what happens at the endpoints, you have to be a bit careful at the ends. Okay, right, so what is this function Ni? What is the graph of the function Ni? So if I have xi, I have xi minus 1, I have xi plus 1, this is Ni as a function of x, it is 0 from a to xi minus 1, it rises to 1 linearly, drops to 0 at xi plus 1 linearly, and is again 0. Okay, because of the shape of the function, these functions are called either hat functions or tent functions. You can imagine that if you construct functions like this in 2 dimensions, that they look like a tent, they are called tent functions or hat functions. Is that fine? Okay, are there any questions? Okay, so then we will continue with this in the next class.